Okay? We're doing further calc. You learned an identity in your differentiation, which is if y is equal to natural log x, then it differentiates to 1 over x, right? Okay? You also learned that if the inside was a function, okay, then when you differentiate it, in fact we specifically said ax plus b, but I did say it would kind of work with any function, it would differentiate to f dash x, f prime x over f of x. Okay? So we're doing reverse of that. Okay? We're doing integrating f prime x over f of x to get natural log f of x plus c. Okay, remember it's got to be modulus because you can't natural log a negative value. And that kind of works for the definite integrals. I think it was that we were talking about or something like that. Anyway, so that identity. The issue with this identity is identifying that relationship. Okay, this doesn't work for any division. It only works for the division where the top can be expressed as a derivative of a function of the bottom. Okay, so the top has to be the derivative function of the bottom. Okay, so looking at one, very basic one, as a first example, we've got integrate 2x over x squared plus 3. Okay, is the top a derivative of the bottom?
Yep.
Yes, because the derivative of x squared plus 3 is equal to 2x. Okay, so it's a perfect derivative. Okay, so when I integrate this, I can say that just becomes natural log of a function, which is x squared plus 3 plus 7. Okay, so that's it. That's an easy example of it. So because this top part satisfies that, it works. Okay, let's have a look at another example. We want to integrate tan 3x. Okay. Oh, no. Ah, yeah, this is what the identity that I was trying to the other day. Okay. So we're integrating tan 3x. Is it currently a fraction? No, but what do we know about tan? We can write it as sine. So the first step is to identify that actually tan 3x is a fraction. Okay. Sine 3x over cos 3x. What would be the f of x in this situation? Equals cos 3x. So what is f prime x? What's the differential of cos? Negative. Missing something? 3 sine. Nice. Don't forget, if there is a value inside the trig, you need to also consider what that might become on the outside. Okay? So, is the top a direct derivative of that?
No.
No. So here's where we're going to introduce a k value, okay? Which is what can I multiply this by to make it become this, which you can then factorize out. Okay? So what would I have to times minus 3 sine 3x by to make it just sine 3x?
Negative a third.
Negative a third. Negative a third. So I would have to times it by minus 1/3. So the top line can be written as minus a third times negative 3 sine 3x. All over cos 3x. So this is the same as that. Okay? Yes?
Yep.
Okay? And that means that I can now integrate this. Okay? Where I take k to the front, so minus 1/3, integral of minus 3 sine 3x over cos 3x, that is equal to minus a third times our natural log expression. And I'm really hoping that I've not made some mathematical error there because I didn't actually check to see if that's right. Is that right? Oh, God, I'm actually remembered this. Okay, so most of the time I actually remember. I don't remember this stuff. It's been a year since I taught it last. Okay, so that's basically it. Okay, you work out. You look up two functions, top and bottom. You find the derivative of the bottom one to see if there's a relationship between the derivative and the top. If it is a relationship, and it's straight relationship, you can just integrate it straight away. If it's not a straight relationship because it's not the exact same value, you need to consider this value here, which often gets referred to as k. And then you bring the k to the front of the integral and put in what the derivative was. Cool?
Cool.
Alright. Okay. Let's do one more. Okay. And obviously all of this stuff works with everything else, so your definite integrals and whatever. But we are doing the integral of what's it?
What is this stuff?
I don't know.
Which one is this?
Oh, I'm looking at the wrong page. I'm looking at exercise 8b. I was going, well, that doesn't make sense. That's not what we're doing today. Alright, 3x squared plus 5x over 2x cubed plus 2x cubed plus 5x squared. So again, we need to work out what is our f of x, what is our derivative of f of x, and what is our k value. So you can see it often written like this. Okay, we try and work out a way that this works, try to work out what the k value is, basically. So if f of x is 2x cubed plus 5x squared, then you know that f prime x would equal 6x squared plus 10x. Okay? Is there a way of writing 3x squared plus 5x in the form k times f prime x? So 3x squared plus 5x is equal to k times my derivative. I'm running out of space. What must k be? K equals a half. So I can rewrite this integral as a half times 6x squared plus 10x over 2x cubed plus 5x squared, which means I can say a half times the integral of just 6x squared plus 10x over 2x cubed plus 5x squared, which integrates to a half natural log modulus, 2x cubed plus 5x squared. Okay? For working I've written there is for working. I think generally finding out what the k value is, as soon as you find out that, you can actually just go straight to this, which is the k natural log of the function. Okay? You don't technically need all of those lines working. That's the full working of what I'm actually doing. I'm re-expressing 3x squared plus 5x as the derivative times a value. If you're timesing something by a value, you can actually bring that to the front of the integral, which is this step. And then because I've reached this identity, which matches this identity, I can integrate it. And don't forget, plus c. Is that what you're about to say to me? I can see you itching to say it. Okay? Alright, that's it. Okay? So in reality, it's all about finding k. How can you re-express that numerator as the derivative of a denominator, and what would the k value be? Okay? Okay? Okay. Go on with it. I can't stop saying it now. Just can't stop saying it. Okay.